Last lesson of chapter 10, continuing with numerical methods. So here we're going to compare the difference between what we learned in 10.4 with rectangles with what happens if we use trapezoids instead. So you can clearly see underneath this diagram that I've added. I know it's not in your notes package, but I've just added this in so you can see the difference between rectangles and trapezoids. So in our rectangle method, we've got some space that's missing in our approximation. Now we know from 10.4, the more rectangles we put in, the less that space happens. And then we add in the limit and we end up with a really good approximation. But if we put trapezoids under our curve instead, you can see clearly that they fit a little better than the rectangles and there's less space that is missing. Now I use a pretty steep curve here, but it would still be noted that if I had, like a curve and I'm trying to fit my trapezoids under here, that it's still not a perfect fit, okay? I still have something curvy going on that I'm trying to fit a slanted straight line underneath. So there's still an issue with it fitting perfectly, but they do fit better than rectangles. Okay, so in order to understand this rule that's given to you, this leads us to the trapezoidal rule. Where does this come from? Well, this is adding up all the areas of each individual trapezoid. That's where this formula comes from. So let's unpack it and see if we can understand where all those pieces are coming from so that we know how to use it. And I know, again, this is not in your notes. You don't have to write this down. This is just background so you understand how the formula works, where all the pieces came from. Okay, so let's pull out one of these trapezoids. I'm going to pull out this one right here to have a look at it. And how do you calculate the area of just one trapezoid? Okay, so we have to go back to junior high math probably, and learn that the area of a trapezoid is 1/2 multiplied by the sum of the bases times the height or the width of the trapezoid, okay? And so when you're looking at these, the sum of the bases come from the parallel sides. Okay, those are what builds the trapezoid. So a trapezoid has two parallel sides. So in this case, my two parallel sides are going to be these vertical pieces. Okay, let's call that B1 and B2. Okay, so in order to get this area, I'd have to take half of B1 plus B2, and then I would need to know what the width is between these, multiplied by the width. That's going to calculate the area of one trapezoid. Okay? So then we have a whole bunch of trapezoids, and it's going to tell us how many trapezoids we're going to calculate. So in this little diagram that I've drawn, I have 5 trapezoids. Okay? And so we're going to figure out, how does this relate to my formula? Let's go down here for a sec. Here we go. This is better. How does this relate to the formula that's given to us? Where did the f1, f of x1, and all of those come from? Okay, so I'm going to quickly draw in my trapezoids again. Forgot to do that on the second diagram. Okay, so I'm going to put in, I think it's 5 trapezoids. Here we go. And so this is between the interval of A and B, and I subdivided this into 5 trapezoids. So then what are the in-between subintervals? Well, let's call that x1, x2, x3, and x4. So the area of this trapezoid right here that we pulled out earlier would be, okay, so what would his area be? It's going to be half times his B1 plus his B2. So I need to know, what is this length right here? Well, that is whatever that vertical height is, the y value. Let's call that y1 for a second. How would you calculate that? Well, you would input your x value, you would input your x value into your function. So that would be f of x1 plus, then I need the second base. Let's call that yellow right here. That would be y2 or f of x2. That would get me the two bases, the two parallel sides lengths that I could add together. And then I would need to know what is the width. That last piece is the width. So this is similar to what we did with the rectangles. In order to find the width of every trapezoid, I need to take my interval from b minus a divided by however many trapezoids I have, or rectangles. Okay, so the width is the same. So that would be b minus a on n. That's how I would get the one individual trapezoid's area. So that's just for that one that I pulled out of there to find that area. Okay, so then I have to take that and do it 5 times because I have 5 trapezoids. So let's look at that. So the area under the curve would be 1/2 b minus a on n, that's the width, times, so the first rectangle, this guy here, so the left side, what color, well, you see, left side there would be f of a. That would be b1, right? Plus the right side is f of x1. So that's just trapezoid number 1. Let's use that big T maybe. Okay, plus then I go to the second trapezoid, 1/2 times the width of the trapezoid times the lengths of the two bases, the two parallel sides together, which is what we just did on this example. So that's f of x1 plus f of x2. Plus, you can see the pattern. We would keep going until we got to the very, very last trapezoid. So it would be 1/2 b minus a on n times, when I get to this particular example, it would be f of x4 plus f of b. Ugh, it's hard to fit anything in on this screen. Okay, so this is trapezoid number 2, and then in this case, this would be trapezoid number 5, or it's the last trapezoid. So we have the first trapezoid, then a bunch of trapezoids in the middle, and then the last trapezoid. Okay, so we have all of these subintervals that we need. The x1, x2, x3, x4, those are going to be important when we get to the actual example, when we have to calculate these values that are going into our function. That's where those come in and are really important. We will need to know those numbers. So how does this relate back to our formula? So if I look in every single trapezoid, every trapezoid has 1/2 times the width. So that can actually be factored out. Okay? So the area under the curve is going to be 1/2 b minus a on n multiplied by, what is that piece that's left over? Well, that's all of the base pieces that needed to be added. So when I compare, the first trapezoid has f of a plus f of x1. The second trapezoid has f of x1 plus f of x2. So notice the first one has a single f of a, and the last one has a single f of b. That's a b. But all the other ones are going to double up. I have an f of x1 here and another one there. And that's because the middle trapezoids all share a common side. So the f of a and the f of b, they don't share a side. But when I look at trapezoid number 1 and trapezoid number 2, they share this purple side. Okay, so that's why there's 2 of them. And then when I look at, trapezoids 4 and 5, they share this common side right here. Okay, so both trapezoid 4 and trapezoid 5 need to use f of x4. So there's 2 of them, but only the first and the last ones have the f of a and f of b. So why my formula then goes, I have 1 f of a plus trapezoid 1 uses f of x1 and trapezoid 2 uses f of x1. So really, let's just write that as 2. We have 2 of those. And then trapezoid 2 and trapezoid 3 use f of x2. So I have 2 of those. Plus, I would have 2 of the x3, plus I would have 2 of the x4, all the way till I get to the very last boundary, which would be at b, and there's only 1 of those. So that's where this really complex formula is coming from. So this is 1/2, this is the width of each trapezoid, and then these are the sum of the bases being added up. And where there's a shared trapezoid, they have a coefficient of 2. But the 2 end pieces, the first trapezoid and the second trapezoid, don't share it. Okay, so hopefully this rule makes a little bit of sense about where it all came from. And now we're going to use it in the next video to actually see an example. Okay, so I just used this video to try and explain to you where all the pieces of the formula came from. And really now we have to just understand how to use it. Okay, I'll see you in the next video.